Good morning, everyone. Haha, so you're not dead. Cool. So testing on Android devices has always been a chore in my company and elsewhere. You know, the device fragmentation makes it impossible to touch on each combination of screen size, density, GPU, CPU, and so on. So who has ever tested his application correctly on a few devices? And when it's deployed on a store, an unknown combination of screen size, density, make it crash or not behave like it's supposed to, of course. So when you add to that you have very few devices, but emulators, well, you get the picture. That's why I tried to design a virtual device lab in 2013, which I called Libuli. This lab was never put into production because of network and software limitations. But this year, I'm presenting Podang, another solution that should make it. So this solution uses a farm of real devices. This will help us, and you, maybe, to send your Android devices into the cloud. But no, not this way. So thanks for having me today in Chester for this part of my Mr. What If 2019 tour. So in 2013, we were more and more Android developers ready to test our applications in my company. And to this day, we have around 500 mobile applications. There were already tools to test, but we had to use devices plugged into our laptops or very slow emulators at that time. The real devices were very hard to book and disappeared sometimes, and were often outdated. There is one time when testing manually on your own phone is not scalable enough. To tell you the truth, it was hell on earth. That's when I got the idea of using Android x86 port to crack Android VirtualBox images on demand and to link them with our continuous integration server process, which was Jenkins at that time. We tried to address as many Android versions as possible and made lots of ROM cooking. No, not ROM cooking, ROM cooking. The Android debug bridge, which allows you to connect your machines to Android devices, was limited to 16 devices at that time and binded locally. So we modified the code so that we now had no limit and was able to bind to all IPs. And as Google was about to deliver its L version of their Android operating system, I named that Libuli, which is a famous start of the north of France. Unfortunately, Google did not choose Libuli, but Lollipop. As time went by, I had to realize that our proof of concept could not make it on production because of firewall problems, lack of stability of ADB, and other Jenkins limitations. So, with a heavy heart, I abandoned the project. At that time, a Japanese company named CyberAgent created a product called STF for Smartphone Test Farm. This product aimed at gathering lots of Android devices and plug them into a dedicated server through USB in order to gain control through a web interface. So this was an internal product. We didn't know anything about it. I then switched to other tasks and kept thinking about Libuli because the needs were still there. 3 years ago or so, they open sourced the code, and after some time, it became clear that it could be used outside of its initial scope. Are you doing okay? Great. I was still on some other tasks at that time, but hoped that someday I would be able to tackle this. Fast forward to 2017, I had the opportunity to work again on continuous integration for mobile development and proposed to make another proof of concept. My new colleague had some Mac Mini hanging around. He's the kind of guy you want to have around you if you're into fancy hardware. Anyway, so we installed OpenSTF on the Mac, and we started from that. I already told you about my choice of Libuli, and this time I chose Podang as a name, as at the time we didn't know the name Google would choose for its next OS iteration. But why are we still interested in a solution to test with distant real devices? Aren't emulators much better now? Aren't there lots of devices in my company? Well, we have some devices, but nobody knows who is using them. The emulators are a real pain in the neck within my company because of our security policy or Windows installation. When you launch an emulator, you've got tons and tons and tons of ADB processes which are launched until it kills just your laptop. So we can't use emulators. And even if it worked, how could we use them for our continuous integration anyway? So our proposal makes a heavy use of OpenSTF, but also goes farther, and I'll try to tell you how and why. So F stands for farm. So the first thing to do is to gather some devices, which may be the hardest part. And then you have to plug them into a USB hub, and then you have to link into a Linux computer running OpenSTF. STF supports Android version from 2.3.3 to 9.0, FireOS, CyanogenMod, and other heavily Android-based distributions. Root is not required for any current functionality, though you can control your Android device from within your browser. You have the real-time screen view. The rotation is supported, and you can also type text directly from your own keyboard into the Android device. The touch support for devices having a touchscreen works via software called Mini Touch. You have the two-finger pinch, rotate, zoom, gesture support on regular screen just by pressing Alt and then using the mouse. You have the drag-and-drop installation of APK files, and so that you can launch them afterwards. You can open any website in any installed browser. You can also execute shell commands and see real-time outputs. You can display and filter device logs. Then you can use ADB to connect to a remote device as if it was plugged into your computer, regardless of ADB mode and whether you are connected to the same network or not. Android Studio and other IDE are supported. You can debug your app while watching the device screen on your browser on another screen, for example. You can see which devices are connected, offline, unavailable, unauthorized, or unplugged. You can see who is using a device. You can search devices by phone number, EMEI, Android version, operator, product name, and other attributes with easy but powerful queries. You can have a bright red screen when you are searching for a real device in your lab, when you need to locate it physically. You can also track a battery level and health. So as you can see, the website you get when you install OpenSTF is really interesting when you want to make tests by hand remotely. But that's not really our use case. We want to be able to book and use a device when our continuous integration process has finished building our application. OpenSTF proposes a solution for that, and thanks to the use of their API. It's a simple REST API. So for the authentication, within the web interface, you can create a token that you will use later on with a curl command. So you can log in with just a curl command using that token. Once you're logged, thanks to that token, you can get some information about the available devices, get information about one particular device, about the logged user. You can look at the devices that you booked. Congrats. So 7.39, great job. And you can book a device and so on. So the typical workflow would be log in, get the list of devices, choose one that fits your needs, book it, use it for your tests, and then release it, as you would do with the UI. That's pretty cool. We have a Python script that, with just two variables, will book a device for you and allow you to launch your tests remotely. That's also pretty cool. You don't have to know where the device is located. For us, it could be anywhere in my company's venue, and for your future farm, it could be just about anywhere. You just ask for it, and you get it. I'm not a wizard at all, so let me tell you a few things about the architecture of this project. There are several ways to run OpenSTF. Let's start easy with the local version we use for the proof of concept. So, for the proof of concept, we installed Node.js 6.9 or more recent, ADB properly set up, RethinkDB 2.2 or more recent, Graphics Magic for resizing screenshots, ZeroMQ libraries for messaging, and protocol buffers installed to serialize and deserialize data. Package config so that Node.js can find the libraries. By default, Core OS is the supported distribution, but any Linux distribution should do the trick. As we had an old Mac Mini hanging around, we use this, but it's not a platform that is supported because of bugs in the ADB implementation, but for development and test, this proved being enough. So after installing Homebrew on OS X, which would be Linux Brew on Linux, a few dependencies, we had a local OpenSTF server running. We then had to be able to access it from anywhere, whatever the building may be. That requirement we weren't able to meet with Libuli was a signature of his death sentence. So we have a solution for that, and we'll see later on how important this is for us. So with our first version of the POC, our server was reachable from anywhere, despite being in our office just next to me, and then could be used through any browser in any venue. But wait, even if we stop there, would it be our target solution? I mean, okay, we've got a server, we can attach to it up to 49 devices thanks to several powered USB hubs and USB ports of the machine, but where is the modularity? And where is the failover? Because of the price of the devices, we would have to host the solution in a closed, secured cabinet. One made web server hosting 49 devices in a secure cabinet? What about the network throttling? We could have to send through the network up to 49 videos of the phone screens. And what about the heat generated in a closed cabinet with batteries waiting to explode because of the heat? It does not look like such a good idea after all, rather a recipe for a catastrophe. Fortunately, there is another solution supplied by OpenSTF with slave servers hosting the devices, and a main server will rule them all. So you have to ensure that each of your slave or main servers can handle 0MQ, protobuf, or Docker. So as you can see, there are lots of services, and it's pretty overwhelming. But the reason behind that can be found in the name. STF, which is an acronym for Smartphone Testing Farm. So naturally, this is distributed enough to be deployed at scale. So don't get stuck on this image. It's unnecessarily complicated. It's just there to show that we have lots of different services communicating via 0MQ and protocol buffer. We just have to understand and remember that we have two main roles, the provider and the app. Given this architecture, we can run so-called provider hosts, which are merely the physical machines that you will connect your phones to. These will just run an ADB service called ADB and a provider service. At scale, you will have multiple of these hosts. They will all connect to a so-called app server, which run the other 12 services that make up the STF infrastructure. Now, for the app role, the main server, it contains several units as the authentication, the RethinkDB proxy, the storage plugin, the log service, the WebSocket, the API, and so on, all of them communicating via 0MQ. You can distribute these units as you wish on several servers, but we chose to use just one. So, how does this all play together? The website is hosted by the main server called app. If anyone wants to book a device, he has to log in into his account, and once he's logged, he will have access to the list of devices. This list is aggregated by the app server thanks to all the providers who have available devices. So the end user doesn't know and doesn't have to know where the device is located. That's dead simple from the user point of view. So let's have a look at the workflow and the magic glue that makes this possible. So the device is USB connected and provisioned by the provider, which means that the STF APK is installed. Then the provider notifies the app server over the API service on the 80 port. The end user can then connect to the web page via Nginx service of the app server and choose a device. The end user can then connect via ADB from his computer to the dedicated provider that is hosting the device. It's not directly to the device, but to him it looks like he is connected to the device. So the app server then negotiates a VNC access with minicap protocol of a WebSocket on the port 80 to the provider, and then at the end a stream URL is answered to the app service for VNC access, which is given to the final client to the desired Android device. So there is a special VLAN in our company's office for special needs. The machines in this VLAN can be seen from our development laptop, but also from our continuous integration machines and even from other laptops in other venues or countries. This would not be possible if we were using the office network, because of course the firewalls block communication between the buildings and between the sites too. So this VLAN is also available in the server rooms, which means that we can have machines in our office communicating with machines in the server rooms and the other way. That's perfectly what we needed. The app port of OpenSTF could then be hosted in a server room on a virtual machine, and providers could be then in any office of any building as long as we have an Ethernet plug linked to this VLAN, which is not the case by default, of course. You have to justify why you should be authorized to use it. I'm totally aware that our proposal would make no sense if we don't propose a solution to book devices ahead of time. Let's say that the team is happy with the platform as it is, but wants to schedule a test campaign for a whole week. So what will happen if they can't get the devices they need when the campaign starts? A whole week of tests goes to the trash can? And regarding the authentication, there is a mock-up that you have seen, but there is also an LDAP implementation so that it works with our internal authentication system. So as for the booking, we are checking on the pull request 101 and 617 regarding the ability for testers to book some devices for a period of time in the future. So when a device is booked, we will have to inform the managers of the corresponding providers that they won't be available for anybody but the bookers on that period of time. So what do we have here? With just two variables, you can now book a device, use it for your test as if it was hooked up to the Gitlab CI machine. But sometimes the test can be long, pretty damn long. Fortunately, Spoon, that we already use, is able to do some test sharding. That means that it will be able to use all the devices you can book to run your test. It will slice your test into several groups and then run a group of tests on each device. This way, your test will be finished way earlier than if you use just one device. So this is the way we call the test up to now. We just have to add as many Android STF API lines as needed to book the devices. And there is nothing more to do. The Spoonware script is configured to use auto-sharding so that it will by default execute your test on all the connected devices. So our first proof of concept was working with the Mac Mini under OS X with the VLAN. But as it's difficult to get some money to buy Android devices in my company, so why spend it on some fancy hardware? Furthermore, OS X is not the recommended OS for OpenSTF. You can always install Linux on Mac Mini, as we did later on, but that makes an expensive Linux box for sure. So there comes a NUC. It's a dirt cheap x86 box under 170 pounds that could do the job, but where is the fun? And as I am cheap, well, it's still too much money. So here comes the Raspberry. I already had a few Raspi 3B at home. Who hasn't? By the way, who owns or has already worked with a Raspberry Pi in the audience? Yeah, great, of course. Yeah, more than 90 million have been sold to this day. So I had one with a very bad version of Android TV and another one with Louboutin Mate. The network part is not that good. It's only fast Ethernet after all. And as I had them hanging around, why not try? I thought that not each and every team will be able to afford a Mac Mini or even a NUC. So I did not expect much from it, as it's a slow CPU with only 1 GB of RAM, and overall my experience with Louboutin Mate was quite lame. However, a few years back, I had played with Raspberry Pi 2 and Docker with a colleague, so I knew Raspi were usable with Docker. So with the 3B, it had to work too. So onto the building part now. After a few tweaks here and there, I installed Docker CI on the Pi. I also needed Docker Compose, as OpenSTF orchestrates lots of different containers with Docker Compose. Unfortunately, Docker Compose was not available for Lubuntu, so I had to rebuild it from source with the help of Docker. So you have to build locally a Docker image and use it to generate the Docker Compose binary. Later on, I started everything from scratch again, this time installing Raspbian. It was more natural to use it on the Pi and more performant too. The process to prepare a Pi for OpenSTF was now simpler. Just install Raspbian, install Docker, install pip, and install Docker Compose thanks to pip. Later on, I discovered another distro called HypriotOS. The guys behind that distro called themselves the Docker Pirates to express their rebellious and anti-establishment attitude. As most people were only concerned with Docker on big servers, they went the opposite direction and asked themselves how to use container technology on really small devices. They believe that Docker can be even more useful on small devices than on big servers. I think they're right. So HypriotOS is a minimal Debian-based operating system that is optimized to run Docker. It makes it dead easy to use Docker on any Raspberry Pi by just downloading and flashing a prepared SD card image. So from start to finish, it takes less than 5 minutes to get started with Docker Compose, Docker Swarm, or even Docker Machine on Raspberry Pi. Then I thought I had scored a home run. Just launching Docker Compose with the OpenSTF repository would do the trick, wouldn't it? I was wrong. Even if Docker images can be executed on any platform running Docker, these platforms have to be for the same processor as the one the image has been built for. Of course, images built for x86 can't execute properly on ARM processors. OpenSTF provider image hasn't been built for ARM, neither the other images composing it. So I had to rebuild the main image on the Pi because I had some modifications to make, but also the other images on the dependencies. It was not such a big deal after all. Just create a new ARM image based on Alpine Linux, reference it to build the other images, change a few dependencies, and wait, and vent, and wait, and wait, and after some time you get what you are looking for. So I was pretty happy for 5 minutes until I realized I could not use our continuous integration to build it. All this work around OpenSTF is to make it possible for our users to test their application within our continuous integration. I build my Docker images, my soft, everything with that CI, which is tightly linked to the x86 architecture. So it's not such a good idea to build my images directly on the Pi. So if I can't build them on the CI server either, what in the hell am I going to do? Then I thought, Docker Hub has to be able to build my images as the Alpine Linux image I found was there. I then copied all my repositories to my GitHub account and was almost sure I would get a fresh Docker image for ARM processor 5 minutes later. Bummer! Once again, I was wrong. Docker Hub is also based on an x86 architecture and can't build ARM images. At that time, I just did not get how the Alpine Linux image made it to Docker Hub. I then spent some time thinking of using a Pi cluster to build Docker images, found lots of modifying examples, and then real ARM servers, which looked perfect for the job until I saw the price tag. I made a little bit of research and quickly realized that even if it worked perfectly, it was not such a good idea to put the SD card under such a high level of stress. With a good heatsink, you can torture your Raspi quite a lot, overclock it, make it do heavy computation, but writing often on the SD card will greatly shorten its lifespan. So, what could I do? My CI server can't handle building my images, Docker Hub neither, and doing it on the Pi will kill the SD card sooner or later. Back in 2013, Resin.io, which is now Berlina, ported Docker to the ARM processor. Shortly afterwards, they wanted to use that to offer ARM build to their users. However, ARM server hardware was difficult to find at the time, so they started looking for an emulated solution. Enter QEMU. QEMU is a wonderful project aimed at emulating other CPU architectures. So, how can this be used to emulate a whole container? Since the container can only access its own private file system, the first step is getting the emulator in the container. So this simply means copying the executable in the image. However, building the above image produces a not such descriptive error. The reason for this error is that QEMU ARM is a dynamically linked x86 binary, which requires a lot of other x86 binaries that don't exist in the image. So the loader tries to find the files, but fails, and so reports no such file of directory. So the easiest way to fix this is to use a statically linked version of QEMU, which will have no dependencies on its environment. So creating one is just a matter of grabbing a copy of the source code, running configure with ---- static, and then make. After this, the statically linked executable will be in QEMU ARM, Linux user, and so on. So as you can see now, using the statically built QEMU binary now works within the container. There are several other steps to emulate a whole container, like loading a specific module of the kernel, improving the syntax, and so on. So once all of these steps are done, you are then able to build an ARM image within Docker Hub with that kind of syntax. I then felt like I had invented the fire. Later on, Shippable allowed to build ARM Docker image directly from GitHub sources and, of course, to push them to Docker Hub. I don't have to destroy my SD cards anymore and wait the whole day in order to build a Docker image. I can do it on powerful ARM hardware and for free. So, what do we have now? A working STF provider on the Raspberry Pi with phone connected to it and images built on Docker Hub or Shippable. That's a pretty nice first step in the right direction. Down the rabbit hole now. The OpenSTF ARM image is not up to date with the OpenSTF x86 image, so another long journey began. Trying to update the ARM image proved quite difficult because the updated versions of the different products composing it, with, for example, with ThinkDB, Node, NPM, and so on, were not easily compiled on ARM. So I opened quite a few issues on the various projects. I'm still waiting for fixes on several of them. Then, as I had discovered other Linux distros like Armbian or Hypriot, I began to dig and found that the Raspberry Pi 3B had an old SoC and that there were tons of other more recent ARM SoCs with better performance and lots of other SBC makers that produce other cards that I had to try. So I also had to try and build my own images for the candidate board that I thought would be useful for me, but I've been telling you about SBC without even explaining this acronym. So let me say a few words about that. So SBC stands for Single Board Computer, so a computer made of just one board. These computers are built around a SoC. Yes, another acronym, stay focused. So SoC means that on a single chip you will find a CPU, a GPU, RAM, and other chips that are used to control the board hardware. GPIO, USB sensors, LCD screen, and so on. So most of the time, this card will run a version of Linux based on Ubuntu, but lots of them also can run Android. Android, really? This led to another experimentation, more of that later on. So lots of these cards are really technology jewels for quite cheap. The downside of it is that the manufacturers don't really care about the code quality or documentation. So once that you have bought them, you're really on your own. Orange Pi manufacturer, for example, makes good SBC for very little money, but the OS they ship with it is pretty lame. Their Android version is based on a very old Linux kernel and is not very stable. And their Linux version is a shame, almost unusable. Fortunately, there is a real community of die-hard fans that build regularly kernels for these boards and even complete distros like Armbian. So I've been able to make some tests with some very recent kernels on some of these boards. And there is another specificity that makes it difficult to start tinkering with this board, which is the U-boot. So it's an open source, cross-platform bootloader that provides out-of-the-box support for hundreds of embedded boards and many CPUs, including PowerPC, ARM, Xscale, MIPS, and so on. But if your card is not handled by U-boot, you're stuck. I won't detail it now, but it's almost as if you had to develop your own BIOS for your PC, but without the specs of the board. So we had OpenSTF running thanks to Docker on a Raspberry Pi and giving access to the phones plugged into its USB port. That's a pretty neat solution and quite cheap too, but my curiosity was aroused because the Orange Pi SBC I had spotted were all supposed to be able to run Android. So what if I could use them instead of phones? That would make sense money-wise, starting at £8, and would maybe be better in the long term than phones because of the lack of batteries and case. So why not try making an Orange and Raspberry smoothie? So I then got myself an Orange Pi 1 Plus. So this board is built on the all-winner H6 SoC. It runs at the same frequency than the Raspi and supports the same amount of memory. It's a 4 Cortex A53 cores, and it's an ARM v8. It can handle as OTG, so we can connect it to any computer running OpenSTF. I gave it a good end-user test and hope that it could be seen by OpenSTF like any other Android device. In case this would not work, we could still use it instead of the Raspberry Pi and the Linux because it has more or less the same performance on the paper. So I plugged it into the Pi and waited. The OpenSTF website running on the Pi never showed the Orange Pi. The logs told me later on that a piece of software called MiniTouch was not able to deal with that kind of device. The problem is linked to the lack of touchscreen, of course. So I wanted to try workaround, so I had to build it, deploy it on NPM with Travis, and build another Docker image with it on Docker Hub. A pretty frightening process. So, back to the rabbit hole. To this day, the problem is not yet solved, but at least I have the workflow to make it progress. So, the Orange Pi 1 Plus is then out of the picture for the time being as an Android device. So, where were we at that time? Raspberry Pi is running OpenSTF, but can't handle Orange Pi yet because of MiniTouch. So we are still using a Raspberry Pi and phones. That's cool. But can we do anything cooler with what we have on hand? So what about using the Orange Pi as an OpenSTF provider then? For this project, I decided that cheaper was cooler. So as we use the Orange Pi 1 Plus is less than half the price of the Raspberry Pi, let's go for it. Well, the support in the mainline kernel for this SOC is not ready yet. And the Linux kernel that shipped with it is way too old and too buggy to run Docker. So this board will be very good and cheap at something like 15 pounds for hosting an OpenSTF provider, but a few months from now. So it's out of the picture for Linux too. What about Orange use now? The 1 Plus has an older brother, which is smaller. It's the Orange Pi 0. So it's even cheaper than the 1 Plus. It's around about 8 pounds and supports only 512 megabytes of memory. I was not really confident about this SBC being able to work as an STF provider, but I was wrong. Even if it swaps a little bit, it's powerful enough to handle 4 phones with STF under Armbian. With the latest Armbian developments on RAM management, I think this card could be the target one. As for its use with Android, of course, it suffers the same problem with Minitouch than the 1 Plus. But as soon as the community will have solved this problem, I think the combination of a 0 plugged into a 0 could be the cheapest and the smallest STF farm on Earth. Now, what if we could make our OpenSTF provider beefier? Our target platform is really cheap and good enough for a few phones or SBC, but what if we have more devices to plug in? The CPU power is not enough for more than 4 Android devices, and regardless of the CPU power, if we ever want to get the screen video stream, which is not our use case, the fast Ethernet won't be enough, and the memory is already full. So what are we looking for? A better SOC, faster Ethernet, and more memory. There are lots, in fact there are too many candidates for that job. Even the latest Raspberry Pi, the 3B Plus, supports a faster SOC, 1 GB Ethernet and 1 GB memory. So why not just keep it to our first idea and just use a Raspberry Pi? Well, there are several good and bad reasons. The Raspberry Pi is called by some overpriced piece of and the SOC is quite old, even of the latest 3B Plus, and Raspbian is a 32-bit system on a 64-bit SOC. You can switch to Arch Linux, for example, which has a 64 bits build for the Raspberry Pi, or to HypriotOS, but the community around building distros for the Raspberry Pi is not that big. Armbian doesn't want to touch it because it doesn't use U-boot, but a proprietary firmware. So the major pro of using a Raspberry Pi is its community. And the major cons are its hardware and its price. So what would you choose? Quality or community? Would you like to have tons of people help you make a LED blink, or have the key people help you set up your own Linux distro for a best bang for the buck SBC? Yes, I chose quality. Next, the cool factor. Having something unusual and more powerful than a Raspberry Pi is way more cool. Okay, I admit it is not really a selling point. So this Odroid XU4 is more expensive than the Raspberry Pi, but it supports 2 GB of memory, eMMC, an octa-core CPU, USB 3, and a very recent Linux kernel on Armbian. This makes a top-notch OpenSTF provider. Now, what if we were using exotic pieces of hardware, like Ethernet switch or a TV box? In fact, at work or at home, we are already next to tons of ARM-powered hardware. So this particular piece of hardware is a ClearFog router with a very powerful SOC and 6 Ethernet plugs. So why not use that with OpenSTF to allow for more devices on the same SBC? I know it's not a router, and it's a router, sorry, and not supposed to be running OpenSTF, but I don't care. It's kind of pricey, but HypriotOS is already running on that bit, so it would work just out of the box. But let's keep focused. I said we wanted something cheap. There are tons of cheap TV boxes in the wild, on Amazon, AliExpress, DealExtreme, and so on. These kind of boxes for 16 pounds to 90 pounds. So some of them are sporting a powerful SOC, have lots of ports, and can run Armbian. So for the price of the Raspberry Pi, You can get a working TV box with its power supply and remote control running Android or Android TV and Armbian able. That's super cool. I'm currently investigating this field, but that's not a plug-and-play solution, unfortunately. I don't expect to have a complete solution based on a TV box soon. But that's really interesting to me, as some of them are running Android and not Android TV, as they support OTG and Armbian, which means that we could build an Android device farm just with these TV boxes used as Android devices, but also as OpenSTF servers. What I'd like you to remember from this talk is that if you have an idea and little to no money, you can set up a proof of concept for cheap. You will be able to find recent Linux distros with recent kernels and some SBC with enough memory to be usable for your proof of concept. You could also run various versions of Android or even build your own Linux starting from U-boot and Linux kernel. There are lots of uses for Docker on such small cards as a server or as a client. As some of them implement power over Ethernet, you could just hang them somewhere without any power supply and let them operate. Most of these SBC support GPIO and USB ports so that you can plug sensors or hats on top of them and interact with the outside world. You can also quite easily set them up so that they will work in a cluster. More and more SBCs are launching every month, and as time goes by, more and more of them become candidates for becoming a part of the Podang farm. So for the Android ones, I'm looking for the one which support USB on the go, so that they can be seen with ADB. And for the Linux ones, I'm looking for recent kernels, so that I can get a recent Docker version 2, gigabit Ethernet, USB, and DDR4 when available. But when I find a new card that doesn't have all of these features, but at a bottom price, I have to test it, however. The NanoPi Fire 3, for example, which I have there, has just about everything. Gigabit Ethernet, USB, OTG, and supports the same price tag than the Raspberry Pi 3B+. It's around £30. And it has twice as many cores as the Raspberry Pi. This card has proved being really useful as it works wonder with OpenSTF as an Android device, as it doesn't suffer the mini-touch problem, and also as a provider server running with Docker and the Linux. At £30, it's not really cheap enough for my taste, but it's a serious candidate. And before I present you another card, I'm sure some of you are asking themselves, okay, using SBCs instead of phones does not solve the fragmentation issues, does it? No, no, for sure, it does not. Our first goal was to make a proof of concept for cheap, and it was a success. Our second goal was not to tackle the fragmentation issue, but to quickly set up a device farm on a limited budget. Of course, there were devices spread among the company's venue, but it would take some time to gather them and to convince teams to set up their own part of our device farm. And the third goal was to have a bootstrap, a workhorse, so that the team that don't have specific needs regarding the manufacturer UI, the carrier UI, the battery, or the network could start testing right away for cheap. So to these days, these three goals are met. Now, time for last board. Lafrit board has lots of cool features, but only fast Ethernet. It performs better than the Raspberry Pi 3, but the price tag is totally crazy. It's £4 for the 512 megabytes version and £8 for the 1 gigabyte one. Can you believe it? £8 for a card that is more powerful than the Raspberry Pi and that can run a very recent version of Android and of the Linux kernel. Our microscale farm, which is not this one, and even not this one. Yes, this one. Our microscale farm is a mess. I mean, our microscale farm is not a final one. All these different boards are difficult to arrange properly. So I know I told you about a workhorse, and what I have just shown you looks like that. So it does not look good, but it does work. Each and every month, we could make another study and find a new set of cards within our price range. But for the time being, we'll keep on the Orange Pi 0 set. But I'd like to set up another one with La Frite. So now, get your Raspberry Pi out of your drawer or out of your pockets and install OpenSTF provider server on it with Docker Compose file. Maybe you don't have a server somewhere able to be used as an OpenSTF app server. Bad luck. But you know what? You can use one Raspberry Pi for the app server and as many as you want for the provider servers. But wait, there is more. I tried it, and the standalone OpenSTF server can be used on one single Raspberry Pi. So long for the modularity and long live low budget. I'm just kidding, but that should be helpful if you want to get a foot in the door. So a whole working STF provider and app can be hosted in that kind of device. I don't say it will be fast, but it will work for sure. And the good news don't stop here. Are there any iOS developers in the room? Whoa. Okay, great. Last August, OpenSTF main developers said that iOS support was in their roadmap for this year. And there is an issue open in OpenSTF GitHub repo regarding iOS, and it is still alive with new inputs from last month. So this new effort targeting iOS is not dead, and I have high hopes that it will happen this year. Our project has already hit production. We are currently using it without a glitch. Everything, despite the documentation for the time being, is available on GitHub. And if you already have phones, an old PC or a Raspberry, don't hesitate to start tinkering with that. And maybe let us know when you throw them into the cloud. Thanks a lot for your attention.
Questions? Anyone? No? In that case, let's put our hands together and thank Bruno.
Thanks a lot.